So today we're talking hyperbolas. It's a type of curve. That's the goal, to graph these things. So let's talk about the standard equation of hyperbolas centered at 0, 0. There's two standard equations. The two equations, the first equation, one version goes like this: x squared over a squared. A is just some constant. And then minus y squared over b squared equals 1. Now, which equation does this look like that we talked about just yesterday? It's similar to, it's not exactly the same. Looks like an ellipse, except instead of having a plus between the x squared term and the y squared term, there's a minus. And it changes the look of the graph considerably. Now, the reason we have to have two equations is because if you switch the role of x squared and y squared, you get something like this: y squared divided by a squared minus x squared divided by b squared equals 1. So in the second situation, y squared's the term with y squared in it is positive. So what the heck does the graph look like? Well, if the positive term involves the x squared, it actually has two branches. One branch will open to the left. It'll kind of look like a sideways parabola, but that's not what it is. It's not the same shape as a parabola. And one branch will open to the right. So it'll have two branches. One graph will have two branches. And the center 0, 0 is right here in the middle. If the term involving y squared comes first, then you're going to get a branch that opens up, and one branch that looks like the reflection of the first branch that opens down. They do look like parabolas, but they're not parabolas. The center would be right here in this case, 0, 0. Okay, so is this easy enough to remember? If the x squared is positive, it opens horizontally. What does x control? Horizontal positions, right? So it opens left and right if the x squared term is positive. It opens up and down it opens if the y squared term is positive. Y controls the vertical, right? So that's a way you can remember it. In just a minute, I'm going to show you how to graph this hyperbola by hand. But first, let's do it on Desmos. So I'm going to type in x squared divided by 4 minus y squared divided by 16 equals 1. And you get a hyperbola. One branch opens to the right, one branch opens to the left, and the center is at the origin at 0, 0. Now I want to look at what happens when we zoom out on this thing. So zoom out. Notice what's happening. It's starting to look like two crisscross lines. The two branches are starting to look like two crisscross lines. We can't even tell that they don't cross at the origin. So what's going on here? Why is the zoomed out version of the graph of the hyperbola indistinguishable from two crisscrossed lines? Well, it turns out that every hyperbola has two asymptotes associated with it. Remember, an asymptote is a line that the graph of a curve gets closer and closer to, but doesn't actually intersect, at least not the asymptotes we've looked at. So what happens is we're zoomed out so far on this hyperbola that it's indistinguishable from the two asymptotes associated with it. So we can actually use the graph of the hyperbola to estimate the asymptotes. And if I did that, if I considered like this guy one line going through the origin, even though we know that's not really what it is, that's what the asymptote is, I could find its equation. Look, this point right here, it's going by 100s on the x-axis, so you'd go 100. It's going by 50s on the x-axis. So you'd go 50, 100. It has x-coordinate 100 and y-coordinate 200. And the asymptote does, in fact, go through the origin, unlike the hyperbola. So we could call the slope of this line that increases from left to right The rise would be 200. The rise would be 200. The run would be 100. So the slope of this line from left to right, that increases from left to right, that is 200 over 100, which is 2. If you do the same analysis for this thing that looks like a line from that decreases from left to right, turns out that that will have the opposite slope, -2. And look, I want you to look at something here. If you think about the standard form of the hyperbola that I showed you just a little bit ago, this is what we would call b squared, and this is what we would call a squared. And it turns out, if you think about the square root of 16, which is b, turns out b is 4, and the square root of 4, square root of a squared is a, and that's going to be just 2. And if you look at b over a, b divided by a, that's 4 over 2, or just 2. And that's no coincidence. It turns out that for any hyperbola that opens horizontally, the slope of the line that increases from left to right is going to be b over a. And the slope of the line that decreases from left to right is going to be minus b over a. And so we're going to use the slopes of the asymptotes of this hyperbola to help us graph it by hand in the next example.